You didn't pick? Well, the parts that you gave me, everybody was ready for them. I have on 4 hours of sleep. I saw the bright color and I must have stared at it for 10 minutes. My brain was I was still writing the last one when he said
Okay, so what I'll do today is I'm going to reinforce the concepts of using the call instruction, the return instruction, the push instruction, and the pop instruction. And this is kind of like a precursor to talk about parameters too. What I'll do is I'm going to implement a print hexadecimal program. In other words, I'm going to write a program to print a number in hexadecimal in using assembly language programming. Okay. All right. So when we talk about recursion, how many people are familiar with the concept of recursion? Okay. Well, basically, it is calling a subroutine, from the subroutine itself. Okay. Sorry.
Self-repeating.
Self-repeating. I would just say that it calls itself a subroutine that eventually will call itself. In other words, it doesn't have to be subroutine A calling subroutine A. It can be subroutine A calling B, B calls C, and then C calls A. So eventually, if you can call back to the same subroutine, it is still a recursive type of situation. All right, so we'll go ahead and write this code first. Now, first of all, how do we do this in C? Any ideas?
Function, and then inside of the function, have this whole to the same.
Well, let's go ahead and take a look at the code. Okay, this is not a programming algorithm kind of class, but I do want to show you guys how you can write recursive subroutines just to print a number in hexadecimal. So we'll go ahead and take a look at printhex.c. Okay. And we'll go ahead and include uni std.h so that I can use just the write function. In other words, I'm not going to use printf. It'll be cheating if I do a printf %x in C. Then I will not be illustrating the point that I am trying to illustrate here. All right. So the main program is going to be quite simple. It doesn't really do anything yet. Okay. And then we'll go ahead and write a subroutine to print the number in hexadecimal. I will just say that the subroutine is going to return a void, and we'll say print hex, and you have to give it a number that you want it to print. So we'll just go ahead and say that this is my parameter n, and this is my subroutine. And in main, one way to use it is just to say print hex 0x abcd. So that means when it prints, it should print abcd at center out. That's what I wanted to do. All right. And remember, I want to do this recursively. I don't want to do this with a loop. I want to do it recursively. So when you deal with recursion or a subroutine that can call the subroutine itself, the first thing you want to ask is, when does it stop? Right? Because you have to think about the terminating condition first. Is when does it stop? So what do you think I can pass as n, and we can say that there's no need to call print hex again because I can deal with this. If I tell you ahead of time what print hex is going to do, like each invocation of print hex is only responsible to print a single digit in hexadecimal, which number do you think will not require, or which range of numbers will not require recursion? Well, let's think about this. Okay, so we'll go ahead and think about it, and I'll also use comments in this program so that we can actually integrate the reasoning in here. Okay, if I want to print, let's say, this number here, 0x1df or 1df in hexadecimal, and if each invocation of printx is only responsible to print one single digit, do you think 1df requires the recursion to go a few levels deep? Yeah, because if one level can only print one digit, this one has 3 digits, so that means I need 3 invocations of print hex in order to finish the job. Well, what about this one? Okay, so we'll say this one requires 3 invocations when one invocation only prints 1 hex digit. Okay. What about this? 0 itself. Does it require any recursion?
No.
Nope. Okay. What about the range of numbers the range of numbers where each number does not require recursion? It goes to f. Very good. Okay, so 0 to f do not require recursion because one invocation can print the corresponding hexadecimal digit. All right. Well, that gives us a pretty good idea of how to write the print hex, doesn't it? Because in C we can use the benefit of n here, and then what we can say is if n is, let's say we're only dealing with unsigned. Okay, that makes it a little bit easier to deal with. So we'll just say that this is unsigned n. So we can say that if n is less than 0x, 0 or less than or equal to hexadecimal f, then we don't need recursion. Otherwise, we do need recursion. So in this case, what are we going to do? How do we print the hexadecimal digit corresponding to a value that is less than or equal to 15, basically? It's a little conditional, okay? You need a conditional statement because from 0 to 9, you need to add the ASCII code of 0 itself. But from A to F, you have to add the ASCII code of lowercase a minus 10 so that they will work out correctly. I think we talked about this already in a previous class. Okay, so in this case, we can just say that ch char here is just simply n. Okay, first of all, you have to check whether n is greater than or equal to 10. If so, then you want to return n plus the ASCII code of a minus 10. Otherwise, you want to return n plus the ASCII code of 0 itself. This statement says, this is a condition. This is a condition of a conditional statement. Is n greater than or equal to 10? If n is in fact greater than or equal to 10, then the expression is going to return this value, which is basically n minus 10. Remember, n is greater than or equal to 10 in this case, so n minus 10 will still give you a non-negative number. But the non-negative number will have a range from 0 to 5. When you add 0 to 5 to the ASCII code of A, what do you get? You get A, B, C, D, E, F. Well, do you want to print A, B, C, D, E, F for the values 10, 11, 13, 14, and 15? That's exactly what you want. And then the other case, we'll just add the ASCII code of 0 to n, but that corresponds to the case when n is less than 10. In other words, n is from 0 to 9. Well, if n is from 0 to 9 and you add the ASCII code of 0 to n, what you end up with would be the ASCII codes of 0 at the ASCII code of 1 all the way up to the ASCII code of 9, which is exactly what we want to print as well. So we'll just go ahead and say, okay, that's fine. We have prepared our character to write. We'll go ahead and write it to standard out from the location ch, 1 single byte, and we're done. The big question is, what if n is greater than 15? If n is greater than 15, we need recursion because we need the subroutine to print another digit. The question is, what am I going to do with the recursion? In other words, for this particular invocation, should I print the lower significant digit, or should I print the more significant digit? That's the question. I'm dealing with a number that is greater than or equal to 16, and I am supposed to take care of one digit, and I'll let another invocation to deal with another digit. You can do it either way. There are two ways to handle this. But you kind of have to think about, okay, I'll just write it here so that it's captured at least in the video. Let's think about this number. It's basically 16 in decimal, but when you print this number, the first invocation will get 1, 0. The question is, do we want to print the 0 and then let the next invocation to print the 1, or do we want to do it the other way around?
Other way.
Okay. We wanted to do it the other way, okay? Or maybe not, because with recursion, one cool thing about recursion is it will come back to you, okay? So what we can do here is this. I will say print x. I will let the next invocation to deal with this number. Is that making any sense? Okay. So it's going to print 1 in this case. The next invocation is going to print 1 when the number is 10 in hexadecimal. When it does come back to me, then I'll do the other logic here. In other words, one way to do it is to do it this way. But then I'll be copying and pasting. I really hate copy and paste. Because every time I copy and paste, there's a potential that I'll be copying and pasting a bug. And if I did that, then I will have multiple places to fix, with that particular bug. In this case, it's really easy to simplify the logic, because what I can do, is to take this out of the conditional statement, because this is something that I have to do anyway. So I'm going to take this one out of the loop, and I still want ch to be, to have a local scope so that I can do it this way. Then I can take these two out, right? And my conditional statement becomes this. But let's double check and make sure that it makes sense. This says if n is less than or equal to 15, nothing to do in the conditional statement. Otherwise, if n is greater than 15, which means n is 16 and up, I'm going to let the next invocation to deal with the more significant hexadecimal digits. Yep.
Why don't you just change the if statement to greater than? And
Yep,
then,
that's the next step.
oh, okay.
But I'm simplifying the program, one step at a
Okay,
time.
okay.
But you're absolutely right. If I change this conditional statement, so it becomes like this, then I don't need these anymore, and that becomes the conditional statement. Yep, absolutely. All right. Well, the question is, do you think I can implement this? Well, first of all, does it work? Big question, right? Well, to answer that question, it's easy. We just go ahead and test it. So we'll go ahead and test the program, and I will end everything with a line feed. Okay. How many people think that this is going to work? Okay, GCC-G, just in case it doesn't work. Ooh, it doesn't work. Now, when it doesn't work, you kind of have to look at the output and then go like, why is it not working? Well, you have to look at this, okay? It has an A, and then it has two unprintable code here, and then I think it's a $sign at the end. Well, I already know why it's not working. Maybe. It has to do with, it has to do with when n is actually greater than 15, it's going to do this part just fine. However, when it returns, what is the value of n? N is still greater than 15. So when I get to this part here, I have to be a little bit more careful and say, well, guess what? I'm only responsible for the least significant 4 bits of that number, not the entire number. Okay. So that means when I get back to here, I would have to say, several ways to do this. We can say, there are two ways to do this. I can either use a bitwise AND to mask out the other bits, or I can also use the % equal to 16 to do the same trick. These two statements will do exactly the same thing. Does everybody see that these two statements, ampersand equal to 0xf, will do exactly the same thing as percent equal to 16?
What is the, okay, I've never seen an ampersand equals. What is that?
It's a bitwise AND assignment. If you guys talk about bitwise AND in your C class? No? Okay, then we'll just not talk about it. There we go. Does that make sense now? So n becomes just the remainder of n divided by 16. So I am destroying the parameter, but at this point it's okay because I don't need it in its original form anymore. And this becomes the code, and we'll try this again. Let's see whether it works. Yep.
Can you please show the main function again?
The main function?
Yeah.
The main function doesn't do much. It just goes print A, B, C, D. Yay, that worked. Okay, so I had a bug, but you can also see how I look at my own program to try to figure out what the bug was. In fact, one clue was that it actually printed A correctly. It printed one of the characters correctly, just the other ones are kind of like way off. So now the question is, can I do this in assembly?
Yes, you can.
Well, can I do it in assembly using only the concepts that we have talked about so far? Without using the frame pointer, without using the concept of parameters? How do I do this in assembly? Well, let's take a look at the C version first, and then we'll think about this a little bit. Now, how do you pass information into a subroutine? There's a
Globals.
You can use globals. You can also use registers. Okay? No one says you cannot use a register like EAX, EBX, and so on and so forth to pass information into a subroutine. The only problem with using a register in this case is when I do the recursion up here, I don't want to change the value of n just yet. Okay? I can change the value of n down here, but up here, I need to retain the value of n so that when I get down here, I know how to deal with it. Is that okay? So that means I somehow have to save the value of n. If you want to do the division instruction and get both the quotient and the remainder at the same time, that's fine. But recursion means, every invocation of the subroutine is going to clobber EDX and EAX. So you kind of have to save EAX and EDX on the stack when the recursion is going on. When the subroutine returns, then you pop those registers back in so that you can utilize the results. Okay? So we'll go ahead and implement this program using only the concepts that we have talked about so far. Questions? No? Okay.
You're saying isn't n passed by value?
N is passed by value.
So you can't mess with it anyway inside of your recursions. You're just
But if I do it in assembly using
assembly
only
is different,
only using concepts that we have talked about, then there's no such thing as pass by value because we haven't talked about how to use the stack to pass parameters. But this is a precursor to that concept, so we'll go ahead and take a look at this approach first. So I'm going to change I will save the file again, but this time as printhex.s so that we can just use that version. And I can delete everything after this, and then comment everything in here. But by the way, if you use this approach, you have to watch out for certain things. If your file has .uppercase s, that means it will go through the preprocessor. The preprocessor will think pound blah 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 space 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 if as pound if. So if you're planning to do something like this with a .uppercase s program, you need double ampersand just so that the C processor will not see it as a preprocessor directive. But since we are not using .uppercase s, it's not a problem. Okay, so we'll say .start, .text, .global, start, And well, let's go ahead and use EAX to pass our value here. So I'm going to move long 0x ABCD into EAX, and I will call print hex. And then when it's done, it's time for the main program or the entry point of the program to exit the program. So we'll go ahead and move 1 into EAX and a 0 into EBX. Do our software interrupt, and now we can try to implement our subroutine. The entry point of a subroutine is easy. It's really just a label. And to get out of a subroutine is a return statement, or a return instruction in this case. So these two parts are fairly easy, but you have to remember to put in the RET instruction, the return instruction. What happens if you forget to specify or put in the return instruction?
It doesn't go back.
It doesn't end. At that point, it will take whatever location is next to it as if it is a valid instruction and keep going. Okay. Now, when your program terminates like this, it will probably be some, location. The values of those locations, it's probably an invalid instruction. So the program will give you a segmentation fault and say, well, this is not a valid instruction. You're lucky. You will be lucky if that happens. It'll be much worse when you have another subroutine defined after this. Because if you have another subroutine, let's say function f, defined after this, then it will just fall through and it will start to execute the next subroutine. And that makes debugging really, really hard because it is as if subroutine f is also called, but it's not. It's just because without the return instruction here, it continues execution with whatever is next to it. All right. So now that is done, we can go ahead and try to do our implementation. Now, since we already know that n, our parameter, is stored in EAX, the comparison becomes really easy. So I can just say compare long 0 xf, which is our immediate operand. We compare that to EAX, and we have to flip the logic. So if we want to use greater than to get into the conditional statement, we have to use j n a to get around the conditional statement. So we'll just say that this will go to if one end, and then we define the label if one end here. If one end is here. And then here we have to call the subroutine. Now we have to be careful when we call the subroutine because we have to change EAX to n divided by, or EAX divided by 16. So that means we can use a division instruction here. We haven't really talked about the shift instruction, so we'll go ahead and use the division instruction to do the same thing. At this point, I'm hoping that all of us know how to use the division instruction. You have to first make sure that EDX is zeroed out, because that's the most significant 32-bit of the dividend. And EAX is already at the right place, so we are good to go. And we just have to move 16 into another register so that that can become our divisor. So we say div-L EBX in this case. Unfortunately, div-L does not take $16 as a parameter or as an operand. So otherwise, I would have done that and not waste register EBX. And after the division, EAX automatically has the quotient, which means our parameter is set up correctly already. And it seems to me that we can call print hex again at this point. Okay, but I said seem. Okay, so we'll see how this program is going to break. All right, so down here, we have something else. Well, we're lucky. So someone can say, oh, the remainder is already calculated in EDX. We are good. Okay, so we just have to move L EDX to EAX because we want N to be, well, I guess we can just use EDX in this case. So from now on, okay, use EDX instead of N. EAX as N. Okay, so now we just have to implement this portion here. It looks like we have a local variable that we have to implement, but we haven't really talked about how to implement a local variable. What are we going to do? I hate global variables, so let's not talk about it. Well, what we really need is a memory location, right?
Another register,
A register is not a memory location.
but it's temporary.
Well, let's use a register for now, okay? Because I think most people want to do the calculation with a register, so we'll just use a register. And so what we'll do is we'll compare, because this part here is a comparison, so we should do the same thing. So we'll go ahead and say compare 10 with EDX, because EDX is supposed to have the remainder of n divided by 16, which is what we want to use to, in this calculation. And then we'll say jump if it is less than, but in this case we have to jump below because we are dealing with unsigned comparison. So we say JB to if to else, and then the then part, okay, I will just go ahead and know what we are doing here. The if to else part, will handle the other case, which is n plus quote unquote 0. Okay, so we'll do all the calculations using EDX. EDX already contains the value of n, so all we really need to do in this case is to say add L dollar, the ASCII code of A minus 10, just add it to, what is it again? EDX. And we have to remember to jump around the other part of the conditional statement. So we have to jump to if to end, and then we'll go ahead and define if to end over here. Oops. Here. All right. So the if to else has to implement n plus quote 0 quote, which is the ASCII code of 0. So we say add L dollar, the ASCII code of 0 to EDX. And it falls through to if to end, which is fine. Are we doing okay so far? All right, so now we have a right statement here. Oh, we have a problem, don't we? Because we can do everything here. We can move a 4 into EAX to specify this is a right operation. We can move 1 into EBX to specify we are writing to standard out. We can move 1 into EDX to specify we are printing only one single character. But we have a problem with ECX, because ECX is supposed to contain the address of the location that we are printing from. But EDX is not a memory location. So how can I create or allocate a memory location on the fly so that that memory location will have the value that I want to print?
ESP.
We can use the stack, okay? So the stack is the key. Now, since I'm feeling particularly lazy today, I'm just going to say, well, we have to do this before that, okay? Before we change EDX. So we'll push L, EDX. So that means EDX is now pushed on the stack. Once we have EDX pushed on the stack, what am I going to move into ECX? So the ECX is going to be the address of that 1 byte that I want to print. Now EDX is a 32-bit register. When I push EDX, I did push 32-bit or 4 bytes onto the stack. Of the 4 bytes, only 1 byte is what I want to print. Exactly. The stack pointer points to the very last byte that I push on the stack. And because of the little endian arrangement, the byte at the least address, which is the very last byte that I push on the stack, remember the stack grows downward. So that means the last byte that I push is the byte, is the byte that I want to print. So that means I really only have to do this to specify the location of the byte that I want to print from. Do a software interrupt. When the software interrupt is done, I have to kind of remember to clean up the stack, right? Otherwise, the stack is not balanced. And if the stack is not balanced and I do the return, I'll be going to La La Land. Because because at this point, because the stack is not balanced, what is on the stack right now? EDX, right? And EDX is guaranteed to be a very small number because it is the remainder of some number divided by 16. The remainder has to be from 0 to 15. And that's the 4 bytes on the stack right now. If I don't do anything, then return is going to continue execution at memory location 0 to 15 depending on the number. Okay? And somebody's going to say, but I don't believe you. You know, we'll run this program and see what happens, right? So we'll go ahead and see what happens when we run this program. Okay, and the same person who says, you know, this program is going to run is going to be brave enough to say that, well, since the program is going to run, I'll just go ahead and run the whole thing. So just say R, not set up any breakpoint. There's no need to stop and trace anyway. Bing. Okay, well, it seg faults, and it seg faults in a kind of strange way too. It doesn't go to a location of 0. Okay, let's see whether we can change the program just enough so that it will go to the location that I talked about. Because we have 2 problems here. Okay, we have 2 problems right here. I just want to explain one problem at a time. So let's go ahead and simplify this and say, let's not print 4 digits. Let's just go ahead and print something that only has 1 single digit, so that it doesn't have recursion, so we don't have any register clobbering going on that can lead to other problems.
You were in the wrong file.
Hmm? Oh.
Yeah, it was the C file, not the.
Oh. Okay. Right. Go. Assemble, link, GDB again, run. Yikes! We end up at location 30. Now, why do you think 30 is a little bit significant here? What is the 30 is if you look at 30 in hexadecimal as an ASCII code, what is the actual character? It's lowercase a. Now, how do I know it's lowercase a? Because I can do this. Oh, it's 0 itself. Never mind. That means something else is also wrong, but that's definitely one of the things. Oh, it printed 0 here. Okay, that kind of makes sense. That means the logic of the conditional statement is also wrong. It branched to the wrong place. All right, so we have to fix one thing at a time. Okay, now this is a good debugging session because I actually wrote some bugs intentionally, but this one I did not write it intentionally. Okay, and those are one of the best bugs to try to get rid of because I don't really have because I cannot just say that I put that bug here. Well, this one was not intentional. All right, first thing to check is to make sure that when I specify the parameter, I did specify a. So that means when I'm down here somewhere, this decision path was wrong. Okay, it made a wrong branch at some point. I'm thinking. Okay, let's do the comparison again. So we're comparing n, which is the remainder of n divided by 16, with 10. Okay, so that part is good. And according to this, we jump to if to else if n is below 10. We go to the else label here. We add the ASCII code of 0 to EDX. And then we print it out, and we get a 0. Otherwise, we do not do the branch, and then we add the ASCII code of a minus 10 to EDX, and then we branch to if to end, which is over here. So I can't really quite explain why the program is not working, so I have to cheat again and use GDB to debug the program. Now, would that be cheating? I mean, if you are actually working and you use GDB or a debugger to help resolve why the program is not working, that's what it's for. right? You know, GDB stands for goddamn bug, but also, you know, the to-do debugger, right?
What happened to the pop though? I mean, I thought that was the reason why we were.
No, the pop accounts for something else. The program crashes because of the lack of the pop. But it prints 0 instead of A,
I
and
see.
that's a logic problem.
Okay.
So it has a logic problem in this code. Okay, just have to make sure it's dividing. Sorry?
Where would it get 0 from?
Correct. Well, we don't know what it is, you know, why it's getting a 0, so we'll go ahead and use GDB for this debug session. And I feel confident enough that we can just, you know, put a breakpoint on line 14 first. So we'll run the program, we're on line 14, and single step. It did branch to if one end, which is correct. It did not go for the recursion. That part is correct. And then we look at EDX. Okay, let's say IR EDX. EDX is 0. The remainder is 0. And EAX is 10. So that means I did not perform the division operation. That's right. I did not perform the, because I branched around the division. Oh. Okay. You can see how, you know, just by tracing 2 steps and looking at the registers, I can realize, hey, something is wrong already at this point. So, but it was right before, so now I can narrow down, you know, where the bug was. Okay. The problem has to do with I performed the division only in here. But over here, I'm assuming the division has already happened. So what I would do is to take all 4 statements and we'll put it out here. Oh, this one has to stay in there. Ah. Okay, I think I just. There we go. Okay, do you guys still remember what is pop F and push F?
Nope.
It's our status flag. It's the flag register. In other words, the flag register contains all our carry, 0, overflow, and the sign flags. And what I'm doing here is I first perform the comparison, and then I say, okay, I need the flags back at some point, so save it on the stack. And then I proceed to, you know, do the division. After I perform the division, then I pop the flags back so that the JNA instruction can utilize the flags that were set by the compare long instruction instead of the division instruction. But I cannot do the division first because if I did the division first, then the comparison will be using the quotient of the division for the comparison, and that would be wrong as well. Is that okay?
So no matter what number you have in there, in the EAX, it's still going to divide it?
The EAX is changed already. The division instruction would have executed already by this point.
Well, no, I mean like the comparison first. You compare, and no matter what the result, you're going to divide.
Yes, I will do the comparison. I will do the comparison first, but I'm not going to use the flags immediately. So I'm saving it. I do the division. I pop the flags. Then I do the conditional branch, which is based on the comparison of the original EAX. Okay. So this program is going to be, you know, fixed to a certain extent here, but it's still not going to print the right thing. We'll go ahead and use GDB, and forgot to specify the program name here. Hex. Run the program, and this time it prints A correctly, and 61 in hexadecimal is the ASCII code of lowercase a. But the program crashed. But when it crashes, look at where it crashed to. It matches the ASCII code of A, and that's because we push that register on the stack. And by the time we do the return instruction, that's still on the stack. And the return instruction is not very smart. It doesn't say, hey, this doesn't look like a return address. It has to be wrong. It just grabs whatever 4 bytes that the stack pointer is pointing at that point, and then say, oh, these 4 bytes will tell me where to continue execution. And now it's trying to continue execution, at location 61 in hexadecimal, which is a place where your program, your end user program, does not have access to, and therefore you have a segmentation fault. Okay, so why do you think I put this bug into this program, intentionally, even though I knew that the pop-L, is missing? The other bug was unintentional, but I found it, fixed it. Exactly, to show you, what happens when the stack is not balanced. It will try to continue execution at a location that can be anywhere, depending on the content of the stack at the time. By looking at that location, it might give you some idea of, oh, my stack pointer is off. It is actually pointing at something else that I pushed on the stack, and then you can, from this, now you can tell that it was just the EDX that we were pushing on. EDX. It was the EDX that we pushed on the stack earlier. All right. So how do we fix this problem? Let's take a look. The problem has to do with this push doesn't have a pop to counter it. In other words, there's no pop, and these 4 bytes that should not be on the stack by the time we get to return is still on the stack when we get to return. How do we get rid of these 4 bytes? We can pop, but what other ways can we get rid of the 4 bytes? Because I don't really need it anymore. Those 4 bytes is only there so that I have a place to print from.
Can you reset ESP or?
Yep, exactly. We can just say add L $4 to ESP, and now the stack pointer is pointing 4 locations up again, which means those 4 locations are now quote-unquote deallocated. All right, so let's try this program and make sure that it doesn't crash anymore. Okay, that's the whole idea, is for this program not to crash anymore. So we'll assemble, link, GDB, and now we have a renewed confidence in the program. You just run the program, and it prints A, and then it exits normally anyway. Okay. Inferior, yes, inferior 1. I think that has to do with the value of some of the other registers when it exited. But it did print the correct hexadecimal digit. Now that we know that we can print 1 correctly, we get more confident, and then we try to print maybe 2. Okay. So we'll go ahead and change the program and say, what if this requires 2 digits? Run the program. It printed A1. Not AB, it's A1. Yep, go ahead.
Why are we adding and not just using pop?
Because I don't really exactly have a place to pop it to.
Okay.
Now there are 2 concerns here. One is, yeah, you can just I could have just popped it into a register that I have no use of. For instance, I can say that in this case maybe EBX has no use. I can just pop L, EBX. But that is actually slower compared to add long $4 to ESP for one important reason. When you pop, you are actually using an implicit memory operand because everything on the stack is in memory. So when you're popping into anything, you have at least 1 memory access from the stack. So when you say pop L EBX, you are actually going to the stack, which is a memory operation, grab those 4 bytes and copy that to EBX. The alternative, which is add L $4 to ESP, does not involve any memory operand. So that means your cache of the processor will not get unnecessary, will not try to get something unnecessarily. So that's why the operation is actually slightly more efficient in that case, but only slightly. Besides, I don't have a place to pop it into. So why do I want to destroy the value of a register unnecessarily? Okay, that's a good question. But the program stopped working. Okay, the program stopped working. So what I want to do is to find out why the program is not working. it doesn't seem to do anything that's crazy anymore. So I'm kind of confident the stack is balanced and the return is actually returning to the right points. But I'm not quite so sure about the thing that I'm printing. In other words, when I'm printing, let's see here, continue to go. So what I'm printing here is wrong. EDX for some reason has the wrong value. So we'll go ahead and this time we'll put a breakpoint on, let's say, line 31. Okay. Now, whenever you debug a program, you have to know what you should be expecting at this point. This is our first invocation. Well, this is actually our second invocation already, because remember the algorithm is recursive. The first invocation says, oh, the number that I'm supposed to print is AB. It is more than 15, so it will do the recursion. So this is actually in the second invocation already. The second invocation is supposed to print what?
Supposed to print B.
No, it's supposed to print A. The first invocation, every invocation prints the least significant 4 bits. So the first invocation is supposed to print B. The second invocation prints A. This is our second invocation. So we'll go ahead and take a look at EDX. So IR EDX. It is A indeed. Okay, so it seems like the program is working just fine. So we say continue execution, and now the recursion is done. We are back to the first invocation, because the recursion happens first, and then it is my turn to actually print something. So when it is my turn, I'm the first invocation. I'm supposed to print the least significant 4 bits of AB. So in this case, I'm supposed to print the B. So EDX is supposed to have B, which is 11, but it only has 1.
Wrong register.
Oh, EDX. Okay, it's still wrong. It is still wrong, but why is it wrong? I didn't do anything to EDX. The first invocation says, I performed the division a little bit earlier. I am supposed to have the quotient in EAX, and I'm supposed to have the remainder in EDX. But my EDX is gone. It's not there anymore. Okay.
You moved 1 into it during the right function.
That's right.
But I haven't got to that point yet.
Yeah, you already wrote the egg.
The second invocation, right? The second invocation modified EDX already. So that is why. All right. So now that we know that EDX was clobbered, basically, and clobber is a technical term for this sort of situation, what am I going to do to protect EDX? And when do I do that to protect EDX? Let's go ahead and take a look at this program. Wait, what is the problem? The problem has to do with this instruction here destroyed the content of EDX. But that's not the only thing that destroyed EDX. Because in the second invocation, we also have the division instruction, which also destroyed the content of EDX. So what is the key? How do we fix this problem? Okay, so I'm one subroutine, and you're another subroutine. Okay, so I'm one subroutine. I'm doing the division instruction. I say EAX is important to me. I'm going to use it later. EDX is also important to me. I'm going to use it later, and then I hand over the registers to you as the second invocation. You have no idea that I needed those registers. So you do whatever you want to do with those registers, right? And then control gets passed to me, and it's the same set of registers. It's not like I have one set of registers, EAX and EDX, and you have another set. It is the same set of registers. So when I get the registers back, my EDX is gone, right? So how do we fix that problem? Maybe I should do something like this. EDX is important to me. Before I pass control to you, I'm going to write down the values of EDX on a piece of paper, save it first, and then I let you execute. Then you can do whatever you want with EDX, because guess what? When you're done and control is back to me, I'm going to rewrite EDX with the saved value that I have saved earlier. Are there any instructions that we have talked about that can do this particular task very, very easily?
Push and pop.
Push and pop, exactly. So the easy way to fix this problem is push EDX, which is the only register that I need at this point, and pop EDX back, like that. Okay. Save the program again, assemble, link, and we'll just go ahead and run the program because I'm very confident that it does work. Abuser, very good, very nice. It's AB followed by user, but it is, it's just sounds like abuser to me. That was not intentional.
Can you do
Yep.
me a favor? I'm not quite. I understand what you're saying, but I don't understand. You've placed it in there, the push and pop.
Right.
Can you go through for me, just kind of quickly, the EDX and how you're saving it? Because it
Okay.
seems like before that you're moving 0 into it.
As
I'm getting
the
confused.
okay, it has the remainder that I
Oh, but
need
thanks for
later.
going over that.
Okay. Print hex is going to change EDX. And that's okay because I saved it. So now it's retorted. Just have to restore now. Is that okay? In other words, before I call a subroutine that I already know is going to change the value of EDX, and EDX is important to me because I need that for the later operations, because I need a remainder for the printing part, right?
Yes.
So that means, if I know print hex is going to change EDX, it's easy to get around the problem because all I have to do is to push EDX on the stack, call the subroutine.
Oh, I see it.
When the subroutine returns, EDX is going to be changed. But that's okay because I just push it on the stack. Now, as long as the stack remains balanced, that means by the time I get back to the pop out instruction, the stack pointer will once again be pointing at the saved value of EDX from before the call. So at this point, when I do a pop L EDX, I get the old value of EDX back into EDX. Then I can continue on with the rest of the subroutine. Yep.
Isn't there another push instruction farther in the if one end, I believe, or if two end?
Another push
Later-
instruction?
Later in the program?
Yes.
You scroll down?
But that's for a different purpose though.
Well, won't this interfere with it at all?
Nope.
Because it's balanced up by the add L4, it was,
Oh,
was
okay.
it 4 bytes back up,
Yep.
so it covered it.
That's our open parenthesis, and this is our close parenthesis. A push should always be matched by a pop, or an adjustment of the stack pointer to account for those bytes.
So when this push happens, there's actually two things now on the stack, right? And it's gonna get pushed back to just being one thing on the stack?
3, because you have the call also.
It depends on, are you looking at from one single invocation's perspective, or are you looking from the overall
Yeah.
program execution perspective? Overall?
Yeah.
If you're looking from the overall program execution perspective, okay, this is what happens when you look at the entire program execution. Okay, so we have the first invocation of print hex. So that's basically a call instruction. So we use 4 bytes on the stack already for the return address. Okay. Now within the first invocation, we push F and then we pop F immediately, so that one is balanced. Okay. But right before we do the recursion, we push EDX, we push L EDX again. So that means we have another entry stored on the stack. When we get into the second invocation, it will do the same thing again, but the recursion is not there, but it will do the push L EDX before the system call to write. So at the deepest point of the stack, we would have used 12 bytes of the stack in this program.
Don't you have a push L though before the first call?
before the first
Before
call.
the first print hex call, you added the push L for EDX.
Yep, that's this one.
It should come before that though, before it ever reaches the print hex. You added the push L to save the value.
You mean this one?
Okay, from the main.
Yeah. Yep.
Okay,
The
yeah.
main doesn't really do anything.
That's right.
Yep. So that means this program in the worst, when it uses the most of the stack, it's only using 12 bytes of the stack. Right? Any questions about this program? Now this is a good program to really read and try to understand because it's using the stack and the push and the pop instructions in ways that real programmers actually use the stack for. I mean, handwritten programs typically would use the stack in this particular fashion. Yep.
There are any limitations to the stack as far as how much information you can store there?
Like the maximum space of a stack.
Yeah, it's just,
How far you can push it.
sure.
Let's write the program to find it. Okay. Okay, we'll do a vim stack limits. Stack limit.s and dot text dot global start. Oops. Start. We'll put a no op here just so that there's a place to put a breakpoint, and we'll do a push. This is the easiest way to do it, right? This program will try to call itself again and again and again until it runs out of stack space and just poops out. Okay, so we'll go ahead and test this program. Now, if you run this program without GDB, it's really meaningless because it would just simply crash, but it doesn't tell you when it crashes or what the stack pointer it was, initially. So that's why it makes sense to use the debugger for this program. So we'll put a breakpoint on line 4, run the program. It stops at the first no instruction. We take a look at ESP at this point because there's nothing on the stack right now. Because if we did not take this value, then we can only see the end value of the stack pointer, and we would not be able to figure out the actual size of the stack. So now that we have a base number, we can go ahead and delete breakpoint number 1. Otherwise, it'll be a lot of continued execution. And we'll just go ahead and continue. So right now the program is chewing up stack space as quickly as it can. And we can probably just kind of move on and talk about some other stuff as it is trying to chew up the stack. It doesn't take very long, typically. All right. So what else do you think we can use the stack for? Just about everything else,
Yeah,
okay?
You already showed we can move flags, we can store points on it.
Mm-hmm. But regarding how to write programs that can integrate to C programs, what else do you think a C program will use a stack for?
Local variables.
Local variables. How about parameters?
Passive value.
Okay. What about parameters?
Ugh.
But we just demonstrated how to use EAX to pass a parameter. What is so wrong with using registers to pass parameters? How many registers have we got? Well, in all there are maybe 8, a little bit more than that. But it's still a very limited number of. It's still going. It's still chewing up the stack.
They work for simple programs, but more complex programs.
Exactly. Having a limitation of a fixed number of bytes, as parameters, is just not a good idea. Okay? Because in C, you can also do something that is really, really nasty. Because in C, you can pass structures by value. So if you pass a structure by value, you can have one single parameter, but it takes up this much space. And you only have this much register space. So it's not a very good idea to rely on registers to pass parameters. So we'll go ahead and I'm going to let this run. But before we move on, I'll just go ahead and take a look at ESP. IRESP. And it's getting a little bit lower, but it's still very slow. But we'll just let it go. Continue. Continue. There we go. And then we can just move on to another window so that we can keep that one. We can keep it, you can keep cooking here. It's just like those infomercials, selling those, elephants and whatnot. They'll keep one, cooking and then move on to talk about something else, and then miraculously, it'll be done right at the right time. Yeah.
I think we talked about this when we talked about the stack window the last time.
Mm-hmm.
But like you were just running a separate session of, it was GDB for another application, and you checked the placement of ESP, and it was much lower. So how come then when you're running an application and two of them are making use of the stack at the same time, they don't tend to crash?
Because each application has its own stack.
But did you just check in a different session of GDB?
Correct. In fact, if I use GDB multiple times, they will show the same address, because each program that you run has its own address space, and that address space to your program looks exactly the same as the address space to another program running under GDB.
So it's instantiated? It's instantiated.
Correct. The system has, it maps memory in a certain way so that your application program will look at its own quote-unquote logical memory locations basically the same way every single time you run the program. All right, and it's still cooking over there. So we'll go ahead and take a look at the second program, and this time we will talk about how to pass parameters on the stack. So we'll look at a very simple one this time. Okay, simple.c. So we'll look at the C code first, and then we'll talk about the equivalent program written in assembly. So this one, let's say that let's make this one kind of interesting. Okay, even though it is simple, it illustrates two concepts at once. All of these concepts are in the notes already. So if you have been reading the notes or will read the notes, they're all in the notes. But we'll do something like this. Okay, simple is really not very smart, and that's what it's doing. Okay, let's make it more fun. Fine. That's what it's doing. And in my main program here, we'll go ahead and use global variables for now because we haven't talked about how to use local variables. So we have an int x, which is my global variable, and then we say x gets simple, 20. Okay. So the end result of this program is pretty easy. The global variable x should end up with a value of 21 because the subroutine returns 21, and we have the assignment statement, and so that's the result of the program. I'm not even going to do any printf, because this program is simple enough that we don't really need to verify its execution. The question is, how do we do something like this in assembly in a way that is compatible with the way C specifies parameters? In other words, this is what I want to do. I want to turn this code into assembly and make the program run even though half of it is written in assembly and the other half is written in C. Does everybody understand what I'm saying? So I'm not interested in converting the entire program into assembly. That's pretty easy. You don't even need to understand how to pass parameters in that case. I'm going to write the program half in assembly and half in C so that this portion will be written in assembly, but it works with the other portion that is written in C. Is that okay? So that means when you write it in assembly, you have to play by all the same rules as the C compiler. The C compiler makes certain assumptions, and you have to play by the same rules. So we'll keep this window open, and I'm trying to do a vertical split, and then on that side we'll save it as simple.s. That. this is my assembly program, and I want to find out how to do this. One thing we have to understand at this point is parameters are pushed on the stack. In other words, when you're dealing with the C code here, when you're dealing with this particular line, what the C compiler is doing is pushing 20 on the stack. Push L $20. It pushes the parameter on the stack, and then it calls the subroutine simple. Okay? In other words, that's the agreement between the caller and the callee. Parameters are on the stack, and they are pushed before the call instruction. That makes sense because you cannot really push anything after the call instruction. After the call instruction, control is already in the subroutine that you're calling. So anything that you want to push as parameters must be done before the call instruction. Okay. So inside the subroutine, okay, so we have the subroutine here. We want to say .global simple because we have to export the symbol simple to the linker. And then we have symbol as a label. And this is what I always do. You know, when I write the subroutine, I always put in the return first so that I don't forget it later. For simple subroutines, it's pretty easy to spot, oh, where's the return, right? But if you have a longer subroutine, it's pretty easy to forget the return instruction. And then your program goes all wonky because it's actually continuing execution onto the next subroutine. And it's just not worth that time if you just put in the return right away. That avoids that particular problem. All right, so now we have two questions. If the parameter is pushed on the stack, how can I access it here? Well, if you do a pop, you are going to pop the return address first. Because the push of the parameter goes first, and then we have a call instruction. The call instruction has an implicit push of the return address. We can access it through the stack pointer directly. But where exactly is it from the stack pointer?
Well, just take out the call address.
Right, exactly. So what we need to do here is to take a look at what the stack looks like at this point. What the stack looks like at this point is parameter x is here. It takes up 4 bytes. And then we have the return address because of the call. So, and the stack pointer is pointing to the least significant byte of the return address. Are we doing okay so far with this picture? So that means ESP is pointing to the least significant byte of the return address. ESP plus 3 is pointing to the most significant byte of the return address, which also means ESP plus 4 is pointing to the parameter. All right. So that means if I go into the simple subroutine, if I do a move L for ESP into EAX, EAX will have the parameter X. Okay. So I want to do the calculation, add 1 to EAX. I'm almost done. I have the result. I have X plus 1 now, stored in EAX. The next question is, how do we return?
Should have put it back on the stack.
Nope. The return value, well, that part depends on the compiler. Okay. But as far as GCC is concerned for 32-bit applications, EAX is how it returns a 32-bit value. So we are done.
So it's actually in the stack now?
Sorry?
So you actually did modify the EAX?
No. Well, I modified EAX, but not anything on the stack. This is a peek operation for paren ESP. It's just peeking in the stack and say, oh, what else is there on the stack? But I'm not removing anything. I'm not adding anything to the stack. So there was no change to ESP itself. I'm just looking into the stack and say, okay, ESP points to the return address. If I add 4 to ESP, it points to the parameter that is pushed on the stack. Okay. Yep.
Okay, well, every program will use %EX or returning the parameter.
As long as you're returning a scalar that fits in 32 bits, yes.
So what do you do if it's not?
If it's not a scalar, I do not know yet about what if you return an 8-byte thing. if you return an 8-byte thing, I'm suspecting it is going to be stored in EDX, EAX. EDX stores the most significant 32 bits, and then EAX stores the least significant 32 bits. If you return a structure, on the other hand, then it's stores somewhere else. Okay, we'll just put it that way. You know, we are going to talk about that too. What if you're returning an entire structure? But this is easy. You know, we're easing our way into the convention of C programs. Okay. All right. So, should we go give it a try? Yep.
So it always return EAX whenever a program returns something.
If you're returning a 32-bit scalar, like an integer or an address, it is always using EAX to return it.
What happened if it's two return type? So you know how we use pointer and C to pass back to a variable.
Well, a pointer is also 32-bit, so if you're returning a pointer, it is also returned by EAX.
No, but it's two instead of one. This is only for one.
But you can only specify one type as the return type.
Not my value, my address. Reference.
But this is the return type. We are only talking about a return type here. In other words, you cannot say, you know, int, you know, simple. This doesn't work. You cannot return two different integers.
I'm not talking about this case.
Okay.
I'm talking about a different case where you're not using like return something, but you're just changing it and pass back the address or was by reference.
Oh, so you're talking about something
There's
along.
more than one variable.
So you're talking about something along the line of this,
Yeah.
but you just have to use it as a pointer then. That's a good question, but we are going to focus on this one first because we want to focus on this simple program to make sure that we understand, you know, how, you know, we can pass parameters on the stack and how the return value is actually returned by EAX. So we want to verify this program first before we move on to talk about what you just mentioned. So we'll exit this one, and this time I have a problem because now they're both called simple. So we'll have to change one to simple c.c. Okay, and I'll just be very lazy in this case and use GCC to do everything and not use a makefile. As X is undeclared in C version. That's because I accidentally deleted that line. Okay. So now we have the whole program, you know, assembled. Linked, compiled, assembled, and linked. Okay, there are three processes combined into one. So now we can GDB the program, GDB simple that. So we'll go ahead and put a breakpoint at simple. Okay. When you say be simple, what it does is it will put a breakpoint at the label simple, which is the entry point of the subroutine in this case. So we run the program, and right now we are at the very first instruction inside the subroutine. The first thing we want to do is to double check what is on the stack, because the whole thing is hinges on the fact that I think that the compiler will compile code and it will push the parameters on the stack before it calls. So we can double check and verify that because we can do an X command. We want to print 2 words, each one as a hexadecimal, and starting at where the stack pointer points to. Does that look about right to you? The address, the lower one is in return address. That seems right to me. Okay, it seems to be in the right range for that thing. What is 14 in hexadecimal?
20.
That's our 20 in decimal. So we just found our parameter on the stack. And in fact, it is at the right place that we thought it was at. So now we can single step within the subroutine. Well, let's make sure that EAX ends up with the same value, 20, which is good. We add 1 to EAX. EAX is now 21. And then we single step the return instruction. Now we are back to the C code. In other words, X should have gotten a value of 21 at this point. Well, let's go ahead and print X. And sure enough, it has a value of 21. So we have just used a very simple program to illustrate two aspects of the agreements between the caller and the callee in C. We talked about how parameters are pushed on the stack and how a value is returned by EAX. Well, the next question, a very natural question, is something like this. We can call this less simple because it is less simple. And we won't have enough time today to finish this one, but I'll go ahead and start on it. You guys should read the notes so that you can kind of understand how the whole thing is supposed to work. And then this is still cooking. So we can see that, oh, it did fail. Very good. Yay. Okay, so what we want to do is to look at ESP again, and it is that value. If you do the subtraction, that's basically the size of the stack, that is the maximum size of the stack that is available to your program. So we'll go ahead and say print.
Isn't it further up?
Yeah, it was further up. That was our middle check.
Oh, that's right. Oh. Well, you can probably guesstimate, the value.
Less than 4
It's 3 megabytes. I mean 8 megabytes or so. Right? Because we have 1,000 million, so it's about 8 million something bytes.
It's a lot of room.
Not if you put like huge arrays on the stack.
I'm just thinking that it's constantly like cleaning it out when it's not necessary, right? So
Yeah, each invocation is only taking up 4 bytes, so it is actually doing this many calls. So we just performed about 2 million calls. Should not have really taken that long, but it took that long because each call is a memory operation. Because each call is a memory operation because it has to push the return address on the stack. Every time you write something to the stack or you read something from the stack, it's a memory operation. So the cache doesn't really help that much because you're sequentially filling up the stack, and the cache doesn't serve any purpose in that case. It doesn't speed up anything. All right, so this part is done. But my question, this is the brain teaser of the day. What if I want to do something like this? So we have int x, int y, and all I want to do is to return x minus y. X plus y is too easy because it is symmetric, but x minus y is not symmetric. In other words, in this case, it is important. Okay, let me just repeat the same program as last time, for the most part, but not exactly the same. So if I want to say x equals sub 50 and 12, you already know the result. 50 minus 12 is 38, so x should end up with a value of 38. The question is, how do you implement sub in assembly? We know how to get to x and y, okay? We just don't know which one is which one. Because we know that stack pointer plus 4 is one parameter, and stack pointer plus 8 is the other parameter. But we don't know which one is which one.
left to right.
Right to left.
Well, go ahead.
Well, I was going to say, don't you need to int y as well there?
Sorry?
Specify y as an integer as well, so it doesn't error, because
No, that's how you specify parameters.
You don't have y declared,
It's
you
a
have x
local.
declared.
That's a
Yeah,
local
it's
declared.
It's a parameter.
As an int.
No, you're just storing x.
so okay.
Yeah, I can use any name, and that's independent of the global variable. Okay, so I'll give you another clue. Okay, I'll give you another clue. Think about this particular subroutine. In C, you can write something like this. I know most instructors do not teach this. Okay, but you can write something like this: void funky, because it is kind of funky. Int and ... you can write subroutines like this in C. In other words, you can write a subroutine in C that has a quote-unquote variable number of parameters. As far as calling funky is concerned, I only have to make sure that the first parameter is an integer. So I can say, funky 2. Then I can use anything here. I can say a character, a string here, another integer, a floating point value, another integer, and so on. The compiler says, hey, it's all good. Okay? So now we have 2 questions, right? We have 2 questions now. The first question is, for sub, what is the order of the parameters pushed on the stack? But it has something to do with the second subroutine.
Can you make all your function prototypes like that?
Yes, you can, but it makes it kind of difficult for the compiler. It makes it very difficult for the compiler to make sure that the calling part is calling it correctly. Okay? Yep.
First goes the return address, and then the first variable, and then followed by the rest of them. Like first it goes to address, then it goes to X, and then Y.
Continue on if you have more and more.
Say again?
It'll push X first because it's the starting point, and then if you have variable, just keep on pushing.
Okay, so well, we are running out of time today, but the mystery is in the notes. Okay, the solution or the solution, the answer to the mystery is in the notes. Okay, so for those of you who are curious, definitely read the notes because these 2 things are closely related. There's a reason why we push parameters in the way we push parameters. Okay. Yep. It's called a cliffhanger. But you know that already because you wrote that note already.